The talk will be separated into parts. First, I'm going to talk about symbolic tensor algebra, and then Itai will talk about vector analysis. So Mathematica has always had a powerful functionality to deal with explicit arrays of components, and the main purpose in this part of the talk is to replicate that from the symbolic point of view. This means that we need a way to specify that something is a symbolic array. And so we will start by showing a few new domains used in assumptions for vectors, matrices, and general arrays. When we work with arrays of any rank, something important is the symmetry. In fact, in physics or mathematics, most of the arrays or tensors with high rank have symmetry. So we will present here a general language to specify symmetries for these tensors. In this way, we will have something which goes beyond what Mathematica had before with respect to arrays. So we need to go back and create a new type of array which understands symmetry. That will be the third part of it. And then we will end up showing how to deal with general tensor, symbolic tensor expressions. I have to say that in this talk, we will use indistinctively the word tensor and the word array. Rank means exactly the same thing as depth, and slots and levels means the same thing as well. We have a new type of domain, vectors, for example. So components of vectors are assumed to be complex by default. We have a function called tensor reduced, and here, because V and W could be general expressions, we don't know that this is true. However, if we say, assuming that V and W are vectors, then we know that this is true. This is the sort of, the generalization of this is what we are. For example, we can declare the properties globally, so that now these things are vectors, and we know that this is true. We know other vector identities like these. We can combine vectors with dot and cross in general ways, and we can do expansions. Here, pairs of cross products are converted into dot products. We can do this in any dimension. For example, this is now we declare that all these guys are vectors in 4 dimensions. So we can do cross products in 4 dimensions. So we need 3 arguments for the cross product. And we know we have this identity, for example, right? If we combine AB, 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 this is 0 for general vectors in 4 dimensions. Right, so this works. Notice that this is a vector is equal to 0. This is a generic thing here. When we work with symbolic tensors, 0 represents an array of any rank. We have a domain for matrices. So now we can have the dimension could be symbolic as well. We have a new slot here, which means symmetry. We can have a matrix which is a square. This means it's a square matrix of reals, and it is antisymmetric. So that means, for example, that now we know that this is minus m, that this is antisymmetric, or the dot with itself is symmetric, etc. And in general, we can have arrays of any rank, of any dimensions, and with any symmetry. This means, for example, it's antisymmetric in slots 2, 3, and 4. Now we can do things like contract the slots 2 and 4, and because they form part of the antisymmetry, this is 0 automatically. And now we can use domains in a different way. For example, we can say, let's have this matrix. Does it belong to this domain? Well, it does if the dimension is 2. Or we can say, does it domain to this domain? Well, it does if these objects are reals and these conditions are obeyed, in particular that B plus C is 0. We can impose more general symmetries. In this case, we will be saying something like, if we exchange slots 1 and 2, we get a minus. If we exchange the first pair with the second pair, it doesn't change sign. We can use cyclic notation or list notation. It doesn't matter. And now we have this big expression here. We say reduce that. This means the only independent component we have is this guy. And all the rest are either zeros or related to the independent component. And we get the relations that must be obeyed, right? So this is a way to check whether something belongs to a domain or not. So that was the first presentation of domains. So let's talk about how general the symmetry can be. So we have these heads, symmetric and antisymmetric. You can specify in which slots symmetric and symmetric are present. If you say all, it will just read from the list of slots which are the involved slots in the symmetry. And now we can specify general symmetries in this way, by generators. This means if you exchange slots 2 and 1, you get a minus sign. So Mathematica knows that that's antisymmetry in slots 1 and 2. If you exchange slots 2 and 1, keeping 3, and you get a plus sign. If you exchange slots 2 and 3, you get 1. Well, that's symmetry. But you can have other symmetries which are not that simple, like this one, for example. Right? This is some sort of, you can cyclically transpose the slots of the array without changing the values. You can have symmetries involving complex numbers. And this means if you move cyclically slots 1, 2, and 3, each time you get this factor. And this number in general can be any root of unity. Some important examples in physics and mathematics of these general symmetries are the Riemann tensor, which can be specified by that. This means flip the first 2 slots and you get a minus, exchange the 2 pairs, you get a plus. Or the stiffness tensor in elasticity, which is also a rank 4 tensor, and it has similar symmetries, but this minus is converted into a plus 1. Just some generalizations. We can also mix all these specifications in some sort of external direct product notation. This means, well, this is a generator notation, and this is one predefined symmetry notation, and this will be all converted into cyclic notation internally. And for those of you who need lots of efficiency, in these computations there is some internal group theory computations going on. Here we can specify a way in which we don't need to do that. This is a strong generating set for those that know what that is. Not every specification is valid. For example, in this case, this is not possible because we cannot mix these 3 dimensions, right? We cannot have dimensions, symmetry in slots 1, 2, and 3 if these dimensions are not equivalent. Then, in this case, this is a permutation of order 3, which is incompatible with flipping a minus sign. So this is an inconsistent symmetry specification. And this is again a case in which is inconsistent, but now each generator is self-consistent, but they are mutually inconsistent. You cannot have an array which is symmetric in the first pair in slots 1 and 2, and antisymmetric in slots 2 and 3. That's impossible. That's only compatible with the 0 array, which is what appears here. Okay, so that's the language for general symmetries. Now, here we have a new type of array which is able to understand all those symmetry specifications. So this has been modeled on a sparse array. For example, we do this. Here we are saying construct an antisymmetric matrix of dimensions 3 by 3, and its component 1 and 2 is A. If we do input form of this, we see that we are using a new construction called structure array, which is a type of array which stores structure and the minimal information to reconstruct the full array from that structure. And here the minimal information is the list of independent components and the symmetry. Now we can do normal of that, and we get what we were expecting. So this is a very efficient construction from the point of view of space storage. For example, in this case, we have rank 7 in dimension 7 array, whose only independent component is this one, and it's fully antisymmetric. We can just take that guy, which stores internally only one independent component, it only needs one. we can say, give me the sparse array representation of that, and it needs more than 5,000. And normal representation, it's quite big. It's 7 to 7 components. In the same way as a sparse array, we can use general rule notation here to construct, say, generic, this is symmetric array, very quickly. So all the indices here are properly placed already. We can say, give me now a random antisymmetric array. And there is a function, tensor symmetry, which is able to compute symmetries. So in this case, it didn't look at the where is it? Here. It just computed the symmetry from this array, right? It can be done for any array. And yes, or vice versa, we can start from a normal array. We can construct its symmetrized array form. And here we will see that it detected that only these independent components are non-zero, only 3, instead of storing all this stuff, and that it is antisymmetric. Right? So that's the idea. So this is an efficient way of storing symmetrized arrays. Together with symmetrized array, we need a number of functions to extract the rules. So this extracts the independent rules, assuming that the rest of the independent rules are 0. And we have functions to know which components are independent. So these are the components you have to worry about their values. If you provide these values, then you know everything about the array. You can do the orthogonal computation, which is give a component, give me all the other components which depend on this one. In this case, there are 8. So for example, if we take our original structure array and say, change this one, which is the same as this one, to square root of pi, we see that square root of pi appears now 8 times, because changing one independent component made us change all components which depend on that one. Okay. Symmetrized arrays contain much structure, and I just want to show you a few plots to show that. So that's, for example, projection to a 2 array of an antisymmetric rank 4 array. So elements which coincide have the same color here. So this is a case in which we have one of these symmetries which is not full antisymmetry, and so we have less zeros, less blanks, and less structure. Or we can have the stiffness symmetry, the stiffness tensor symmetry, which has also a lot of structure but no 0, because there is no -1 in the faces. We can have, for example, a 3D view of antisymmetry, which means just we are breaking the cube into six wedges. Okay. And the fourth part. So let's go back to symbolics. So how do we handle general symbolic case? So first you start by defining or declaring the properties of your objects. Here we are going to have an array A antisymmetric. So remember that A means both array and antisymmetric. M matrix, which is symmetric, and U and V are vectors. And just to compare with explicit computations, we will create objects which actually belong to those domains. So this is an antisymmetric array in the same dimensions. This is a symmetric matrix in the same dimensions, and these are vectors. So now we can do things like, well, in order to do general tensor calculus, we need 3 basic operations. In terms of this, we can construct all the rest. So these are tensor product, tensor contract, tensor transpose. So tensor product is is related to outer, and it does the general case of tensor products. Tensor contraction is a new function to do arbitrary contractions. We can specify any number of pairs to contract. And tensor transpose is the symbolic form of transpose. So we can have something like that. That's the tensor product of our objects. We have the tensor rank of that is 7, because we were working with something with rank 1, 3, 2, 1. So in total, rank 7. given that we knew the symmetries of those guys, we can now say compute the symmetry of that, which means we will have this is the antisymmetry of A, a minus sign if we exchange slots 2 and 3, and a minus sign if we exchange slots 3 and 4. And then we have the symmetry of M. And then we have added symmetry here, because if we exchange slot 1 with 7, we get the same thing, obviously. So we can do contractions now. For example, say we have the contraction of that tensor product, contract the slots 1 and 5, 2 and 4, 3 and 6. Now we call tensor reduce, which knows the properties of the tensor properties of these objects and realizes that this is equivalent to 0. For example, if we multiply these objects with, assuming the values here, then we get 0, right? So this did the computation. Here we didn't do any computation except for group theoretical computations. And the same thing happens with, say, tensor transpositions. So, for example, tensor reduce always wants to sort the tensors alphabetically. So in this case, we had M tensor product A. This was reversed to A tensor product M. But now we need to remember that we have changed the order of slots. Now, if we compare these two expressions, again, with explicit values, we get that they are true. And other operations, other tensor operations, can be constructed in terms of this. And there are others like tensor wedge, Hodge dual, symmetrized, etc. I'm not going to go into the details of them. Now, the key idea here is that the three main operations, tensor product, tensor contract, and tensor transpose, must be always ordered in this way. So we always want to have, as canonical form, here the sorted tensors, a tensor product of them, then a contraction with given pairs, and then outside of tensor contract, a transposition with a general permutation. That's the general case. That's the general idea. If we can convert our expression to a bunch of these objects, then no matter what properties they have, tensor reduce will find whether this is 0 or not. That's the key idea. For example, imagine that we start with that guy. Now we say, well, tensor reduce, we have that. And notice how we have tensor product, tensor contract, tensor transpose in this order. And the tensors have been reordered. Now this is equal to 0. We can check that this is true. Notice that this is a 0 array because the list of components is empty. We have another example in which, again, notice how tensor contract and tensor transpose have flipped. And here we have an expression which is like dot. Here, for example, dot means contract this with the first slot, the second with V, which is exactly like that. And if we, again, compare these two, this one, that one, this one, right? So these are equivalent forms of the same expression. Here, the same thing happens with inner, so we can give a form which is equivalent to inner. Inner has this freedom of choosing which slot of the first array you can contract, and this 2 is equivalent to that 2 here. And well, I have 1 minute for my favorite examples with some more complicated cases in which I just wanted to show how easy it is to construct programmatically tensor expressions. You just have to put tensor product, tensor contraction, etc. in the right order. So this is a case in which we are contracting strings of antisymmetric arrays. And here I'm going to do it up to 70, which means we are handling 140 slots. And this is quite faster, right? So it took 0.2 seconds to handle 140. So for Riemanns, we can do exactly the same thing here. This is a way of constructing a random monomial. So here we have, we start here with tensor product. Then we have a general way of constructing random contractions, and then random permutations for the transposition. So this is a fully random monomial. And now we can construct this sort of expression and do tensor reduce. And well, this is a reduced form of that one, a canonical form, right? So this is the way that symbolic computations work. So that's the first part. I finished. I'll hand now the talk to Itai.
So Mathematica 9 will introduce 8 different functions related to vector analysis, which is perhaps not a huge number, but there are 8 very powerful functions, actually 7 powerful functions and 1 freeloader. It's an exercise to the listener to figure out which one is the freeloader. But there are different ways of grouping them. I've chosen, for the purposes of this talk, to group them into 2 groups. First, I call the calculus or intrinsic group, which do your basic intrinsic differential geometry, graditive, curl, Laplacian, and this strange thing called coordinate chart data. And then a second group related to coordinate transformations, relationships between coordinate systems, and 3 functions in that group. So let's go ahead and dive right in. Starting with some very basic examples, just like D, when you want to take a vector derivative, you give the thing to be differentiated and a list of variables, because right, we're going to be in some presumably dimension greater than 1. You can do dimension 1, but that's a little bit boring. And you differentiate it, you take its gradient, and I hope nobody is surprised to discover that you get 2x, 2i, 2z. Similarly, divergence, you give it some vector field and some variables, you get out a number, you take the curl of a vector field and you get another vector field. In this case, it's a constant vector field, because this is a rotational vector field. And Laplacian of a function, this is another possibly famous result. Okay, so I think we all understand these functions. They're nice to have, although not necessarily revolutionary. One of the things we've done is we freed you from the tyranny of 3 dimensions. So if you want to take a gradient in 2 dimensions, you just take the gradient in 2 dimensions using the exact same syntax. Or if you have a 4-dimensional vector space, a 4-dimensional vector field, you can take its 4-dimensional divergence, and poof, out pops an answer. And here's a Laplacian in 5 dimensions. The one guy which might be a little bit surprising is curl. Probably many people in here are familiar with the 2-dimensional curl, which is more or less just the z component of the 3-dimensional curl. And so here it is -2, much as we got with the previous guy. But we also have the 4-dimensional curl of a vector field. It gives a structured array. We see 4, 4, so we know it's a rank 2 tensor. And it is, in fact, an anti-symmetric rank 2 tensor. I hope I will have some time later on in this talk to tell you more about curl and other dimensions. All right, so coordinate chart data. As the name might suggest, coordinate chart data contains data about coordinate charts. And in particular, various useful properties like the metric tensor, the inverse metric, the volume form, scale factors, things like that. It is designed, again, to be handle general metrics and dimensions. I'm going in this talk to stick to the Euclidean metric, but there is one non-Euclidean metric implemented for version 9, and so, again, exercise for the listener to discover it. So like many of these other pathklets, you may have encountered these, like country data or financial data. You have an entity and then a property, and it spits out a value. So our entities are triples. You say the name of the coordinate system, what metric you're working in, and the dimension. Then here's a property scale factors, and our guys have an additional argument, which is the evaluation point. And so the scale factors at the point 2 pi in polar coordinates is 1 comma 2, because r is equal to 2 and your scale factors are 1r. Now, if you omit the evaluation point, what you get back is a pure function which is weighting to eta point. Whoops, wrong key there. And so here I can give it the point r theta. And voila, if you're familiar with pure functions, this should be very easy to understand. If you're not, just take my word for it. Now, some coordinate systems and some metrics require parameters to be specified. Well, that's pretty easy. You just surround it in a list. The first list is the name of the coordinate system or metric, and the second element is the parameter or list of parameters if it requires more than one parameter. So, now, that would be an awful lot of typing if I made you do that every single time. So fortunately, it understands many abbreviations. So if you give the evaluation point, why specify the dimension? You just look at the length of the variable list. So you don't need to omit that. Since Euclidean is by far the most common case, then you can omit that if you're working in Euclidean coordinates and the Euclidean metric. And you can provide both of these abbreviations at once and just give the coordinates, the Euclidean coordinate system, if you give a evaluation point. Now, there are 3 special coordinate systems, which I think it's pretty obvious why these 3 were chosen, for which, I mean, the standard name is still that long triple, but it always understands just the string. All right, so now that we know something about coordinate charts, what do we have? Well, we have 6 of them in 2 dimensions. We have 15 3-dimensional ones. I call these the Arfken coordinate systems, because if you have the old 2nd edition of Arfken, those are the ones you'll find in there. And they're sort of a very common set for people who do PDE Laplacian things. And we have 3 infinite families. So Cartesian coordinates, not the most difficult to implement, but useful to have nonetheless. That's available in any dimension. Then we have hyperspherical coordinates in 2 dimensions. That's just another name for polar coordinates. In higher dimensions, you have a radial coordinate and then your coordinates on the sphere around it. And we have confocal coordinates in any dimension greater than 1. Confocal is one of these guys which requires multiple parameters. In fact, the number of parameters is equal to the dimension. So the standard names get quite long, but it's all still the same basic principle. These families really are infinite. It would take an awful long time to list all of them, which is why only the first 10 are shown. But if you create a variable list with 20 things and evaluate it, you will find that we do indeed have 20-dimensional hyperspherical coordinates where the first guy must be positive, then you have a bunch of angles between 0 and pi, and only the last one is minus pi to pi. Great. Well, the wonderful thing about these coordinate charts is that you can stick them in the 3rd argument of div, grad, curl, and Laplacian and get an answer in that coordinate system. So here's the gradient in polar coordinates. Since we're always working in the orthonormal basis here, we have to scale it by the scale factors. That's where that 1 over r comes from. The gradient of 1 over r in 3 dimensions, another possibly famous result. Here's the divergence. We have the 1 over r guy, but then we also have this strange f of r theta divided by r at the very beginning. That's because you're differentiating a vector field, so you need to add in the connection term or Christoffel symbol, and that's where that comes from. Again, curl and polar coordinates, we have a connection term and minus sign. The curl of a radially symmetric vector field in 3 dimensions, another possibly famous result. Laplacian and polar coordinates, and in bipolar coordinates. And just for fun, let us take the gradient in 20-dimensional hyperspherical coordinates. And well, we only depend on 2 variables, which is why there are a bunch of zeros in the middle, but we do get out the 2 expected components. Okay, so everything I've talked about till now has been sort of classical vector analysis, and we are not limited to classical vector analysis. This is Mathematica. We like to generalize. So if you take the gradient of a vector field, you get a rank 2 tensor field. And if you take the gradient of that guy, you get a rank 3 tensor field. Similarly, you can take the divergence of a rank 2 tensor field and get a vector field. This basically means our gradient is adding a slot at the end, consistent with how D and all the differentiating functions in Mathematica behave. And so we had 2 slots here. The gradient added a slot, so we now have a 3rd slot, and then we tensor contract the last 2 slots. That's what a divergence is. And so there's another way to get that same answer. We can take the Laplacian of a vector field. Equivalently, that's the divergence of the gradient hint about which is the one freeloading function. And one thing to note is that this vector field, again, this Laplacian is not simply the Laplacian of each component, because that wouldn't take into account the connection terms that you get from a divergence and a gradient. It's what's in classical vector analysis called the vector Laplacian, which in 3 dimensions can also be expressed as grad div minus curl curl. Our system can verify that identity. So I will just very briefly mention, so curl is the Hodge dual of the anti-symmetrized gradient. So you take the gradient, you anti-symmetrize it. That would be a sort of p-form type thing, and so you need to Hodge dualize it. So because you're restricted to forms, this means you're restricted to rank of dimension -1. So if I try to take the curl of a rank 2 field in 2 dimensions, I will get an error message. But if I attempted this in 3 dimensions, I get a scalar out because I gradiented it to get a 3 form, and then when you dualize that, it turns into a scalar. Okay, so that's enough about the intrinsic part. How about some mappings? So coordinate transform data is coordinate chart data with arrows. So why do I say this? Well, if we look at some of the entities in it, we see that they're triples. The second part is a metric. The third part is a dimension. And then we have 2 coordinate systems connected by an arrow in between them. As you might expect, it has useful properties like the mappings, the Jacobian, the inverse Jacobian, something called orthonormal basis rotation, and so forth. It understands all these same abbreviations that coordinate chart data did, and can return a pure function expecting a list, just as coordinate chart data did. Just one quick note, it also accepts this alternate input form. Even though the standard name is the triple, you can give it a rule of 2 triples, and that's interpreted as the mapping between these 2 charts. But that's somewhat redundant since the metric and dimension have to be the same. Okay, so there are 2 very different things that people both call coordinate transformations, which is why the very first long-form tutorial that I wrote for this new functionality was called Changing Coordinate Systems. So one thing you might mean is changing coordinate values. I have this point x, y, and I want to know what its r theta coordinates are. That is handled by the function coordinate transform, which will take a point or list of points and a transformation and transform between them. So r equals 1, theta equals pi over 2 is known as x equals 0, y equals 1. And similarly, these -1s and +1s all have r equal √2 and different theta values. spherical and cylindrical coordinates both share the same phi. It's just the r's and thetas are slightly different. You know, you can do this with the bipolar coordinates. You can do Cartesian to confocal. You get out these big, ugly root objects, meaning I can't give you an answer, so I will just say that the answer is the root of this big polynomial. Some of you have already noticed my shirt, which says, math is hard, so is life, get over it. If you don't like that answer, see shirt. Transform field, despite also being something called changing coordinates, does something completely and totally different and has a very different, a somewhat different syntax as a result. So it takes a mapping and some vector, scalar, or tensor field, and then both the old and new coordinate names. Now these are not points. These must be the coordinate names, and it will re-express your field in the new coordinate system. So for example, x squared plus y squared, root of, is also known as r in polar coordinates. Or if you take r squared sine theta, that's r times r sine theta. R is the square root of the x squared y squared c squared, and r sine theta is square root of x squared plus y squared. Here's Cartesian to confocal, which after the mess of the previous page, it has a surprisingly simple answer, just the sum of the coordinates. So scalars are all very easy to understand. Well, relatively easy to understand. It's vector fields where people get completely confused. So I will start out with a simple example. So here I have the vector field x hat, x, y, z, which when I transform it into spherical coordinates gets r0, 0. So what just happened? Well, we had the vector field x, x hat, y, y hat, z, z hat. We wanted to re-express it in spherical coordinates. If we're going to do that, we'd better also use the spherical basis vector r hat, theta hat, phi hat. This is a radial vector field, hence r hat, and we get r0, 0. This is again quite different from simply transforming each component, which would simply be keeping I hat, j hat, and k hat and re-expressing the thing in front of it. Another example is, this is 0 times r hat plus r times theta hat. So it's a nice radial vector field. We get minus yx, our old friend. Again, not the same thing as transforming each of the components. And example number 3, transforming the radial vector field from Cartesian to confocal coordinates. It has to think for a little while. It spits out that answer. If your dying wish was to know what the radial vector field looks like in confocal coordinates, you now know. If you think that's an ugly answer, see shirt. Okay. So in Mathematica 9 introduces some very powerful vector analysis capabilities. I'm not aware of sort of a competing package that sort of combines both sort of nice, simple div, grad, curl type stuff with actually changing vector fields type stuff. You can sort of do it in Maple if you use pullbacks and push forwards, but I don't suggest you do that in Calculus 3. So we didn't get as many coordinate systems in as I would have liked. This is due to the fact that there are only 24 hours in a day. That's a very annoying fact, but I have to deal with it. But I hope that certainly in our next release, I mean, it's we have the framework in place. Now it's just a matter of entering things. So I hope we'll see more. And I'd like to thank a few people who may or may not be here. But Maxime Ritten, who did a lot of the design analysis and helped improve the syntax a lot. Stefan Ragnarsson, our intrepid SQA tester, and Jeremy Michelson, whose primary purpose was to complain that we didn't give differential forms enough credit, which is true, but again, only 24 hours in a day.